Hello everyone. In this video we are going to discuss about the XOR gate implementation using the NAND gates, universal gate generally. So now in this video we'll just discuss about the NAND gate. So it won't be the straightforward as a basic gates. So here we need to in case of basic gates and all, we'll just implement using by looking at the truth table itself, right? So that is a straightforward because there is some correlation between the outputs of the two gates. So the two gates which are like the one we are going to implement and the one we are going to use to implement. So there is a correlation between the outputs. So we just used to implement only with the use of truth table. But it is not the case with the true XOR gate. So how I am telling, if I understand, if I just write the truth table, you will come to know. So I have A and B, then I have my XOR output, okay, here, and my NAND gate. From this you will come to know. From the truth table, why I am telling, it is unable to implement with that, okay. 1 0 1 1. So here it will be 1 1 and 0. We all know how to write the truth table of that. Okay, we can you can check 1 1 1 and 0. You can check my previous videos to know how to write the truth tables. Okay, so we know now that this is how the truth table will look like. If you see, right, there is nothing at all that actually the comparison, okay, between the output. If you see here 2 high and 2 low for this combination, but here you are getting 3 high and 1 0. So there is none other way to just correlate these outputs, right? So we can, okay, this is one of the method. Truth table is one of the method. So from that we can just compare the functionality of those. So we can able to try, we can try to implement those things. But here it is not the case. So we'll go with the next step, next procedure. So what it is, so the A bar expression, we know, right, already expression, how to write the expression for the particular one, if we know the functionality of that. So here it's a XOR gate. XOR B will be the XOR gate, A bar B plus AB bar. And for NAND gate, we know it is the A dot B the whole bar. This is for the NAND gate and this is for the XOR gate. Okay, so this is what the expression of this one. So this is the expression we are going to implement, but for that only we have this one. So I could have two inputs, it will be NAND, it will be AND and it will get inverted. That is what my cells will do. But I need this functionality A bar B plus AB bar. We have to implement that one. Okay, so we have to derive this one, like how we will do with the truth table, right? So like that we have to just do with the expression now. So for that we need to know about some of the theorems and laws and all we need to know. Okay, we'll just here we'll just list out the things which are all needed for our derivation, but in different video I'll put all the theorems and thing, you can just check it out. Okay, so now the one I am going to introduce here is the Demarcant's theorem. So the Demarcant's theorem, what it is telling, so it will be breaking the bars and it will change the operator. Okay, so A plus B the whole bar, it will convert as A bar dot B bar. These both will have a same functionality. So that is what the Demarcant's theorem was telling. If you break the bars and it will put a different operator in between, you won't be having any issue with it will be same. So that is what the Demarcant theorem telling. And the A dot B the whole bar also, it will be break the bars and putting the different operator. So A bar plus B bar, this is the Demarcant's theorem. Okay, and one more thing I'll tell you. So we have already discussed this, but for your information I will just adding this. A bar of bar will be A. Okay, how I am telling this one? So consider A as a one single input, single bit input. So if I give A for A, if I get 0, my A bar will be, if A equal to 0, my A bar will be 1 and an A bar will be 0, which is same as my A, right? So this is how the double inversion will just play a role of buffer. It won't be anything different. It will just play a role of buffer. So the A double inversion will be A. Okay, so this is what the Demarcant's theorem says. Okay, so now and this one, in this particular law it's saying. Okay, we'll just try to implement this one. Okay, we'll start from here, from backwards we'll go. Since we don't know the input combination here, only we know the output, what we have, we know the gates what and all we could use, and we know the output functions. So we'll just go from the output side of that to derive that. So we need this one, right? But what gate we have this gate. So definitely, actually this is in the form of sum of product, but we need in a form of NAND format. That means product, one particular product ANDed with this. So how we can convert this to this? For that only we are going to use our De Morgan's theorem. Okay, how we could do that? Consider this also, right? Double inversion will play this one. So what I am trying to tell, AB bar plus A bar B, the whole bar will be equal to A bar plus A bar B plus AB bar. It will be same. The double inversion will not do anything logically. Okay, so what we are going to do, we can just double inversion we can do to make this as in order to convert this in order to try to implement this one using NAND gate. So what the De Morgan's theorem says, if it is different, like if you see the OR operator here, this you consider as one input and this is considered as one input. So what you will be having, AB bar the whole bar dot, okay, dot A bar B the whole bar, then the whole bar already there, because double inversion only will not change the functionality. So this is the case. So if you see, this is consider from the upper level only we have to look into. Okay, so consider this is small x, consider this is small y. Here it will be AND operation, then inversion. So the xy the whole bar we can do. So now we have it in a NAND format. So the first NAND gate, what we are going to put it in our output as we have finalized. Okay, so what here x is what we need, a AB bar the whole bar and A bar B the whole bar here at the output NAND gate. So A B bar the whole bar and A bar B the whole bar. Okay, so A B bar the whole bar and A bar B the whole bar. This is what we needed here. Okay, now this is the only thing we have to implement, A B bar the whole bar and A bar B the whole bar. Okay, and what we will be having, only NAND gate. So consider anyway the NAND gate will definitely invert the output of that. So with the NAND gate only we have to implement A B bar the whole bar and again A bar B the whole bar. Two operation we have to do. So for the simplification, to just analyze the initial derivation, forget about the NOT gate and this one, equivalent this one from both of that. So we'll just try to implement the A B bar, okay, with only AND gate available, because now this NOT operation and the bar we have just remove those things to just get a better better understanding here. So just same, right, the A B bar the whole bar we need here. So for that anyway the inversion, the output only NAND gate will be trying to do. So the output of the AND gate, it will just invert and give, same as that case. It will just invert that A bar B the whole bar, it will just invert that one. So the A bar B and A B bar, the one we have to try to implement using our AND gate. Okay, okay, so just we have to implement our A B bar and A bar B only using AND gate. So that is what the expectation. Okay, so consider, because what we can do, just we can add one more NAND gate here, right, with the A bar as one input and B as another. Here A is the one input and B bar as another input, same as A bar and B as one another input, and those inputs will be driven with one of the NAND gate, because the inverter operation also we can do with one of the AND gate, right? Maybe we can cover that later, in this video also we can cover that later, but currently we will be doing with the optimized way. Okay, so okay, like that optimized we will do, then we'll just try, we'll tell that also. So now this A B bar and A bar B we need. So A B bar with only with the AND gate. Okay, available thing is the AND gate. Generally what we will be having as a ready-made input will be A and B, that is our ready-made input. So here if you need this AB bar using here, and here you need A bar, right? So here you need B bar and here you need A bar. That is what you need for this particular A. So what I am trying to tell, if you have used different NAND gate for this to implement this particular NOT gate, it will become again another one NAND gate for here. So 2 already, again another 2, so it will be 5 gates. So we are trying to implement using 4 gates, so we don't need to, we won't be doing it straightforward as that. So what instead what we are going to do, we will be putting one value here, and here that will be common only 1. This will be only 1. So for this one NAND gate only we need, and to do this operation we need another 2. So with the only 4 NAND gates we are trying to implement. Okay. So consider you need your answer here will be, you need for this one you need B bar as output. Finally, if you multiply this, because you need AND gate. Multiply this, finally you need a B bar here. If you multiply with this, here you need A bar. So what could be the value there? Then we already know one more property. Okay, we'll just tell that here. You can have a note of it then. So consider I have one input as 0, and generally AND gate operation we know, right? To make, if any one of the input is 0, my AND gate output will be 0. That is what the general definition of AND gate. So what I am trying to tell, A and A bar. Okay, definitely in binary how many bits we have? Only zeros and ones. So definitely if any one of the input is, if A bar is 0, then A will be 1. A is 0, A bar will be 1. Anyway, any one of these two will get a value of 0. So A dot A bar will be 0. And same as that for OR gate, any of the 1 will become 1 for definitely. So it will be, for sure it will be, any one of the input will be 1. So A plus A bar will be 1. This is some of the property. Okay, A dot A bar equal to 0 and A plus A bar will be 1. This is the simple as that. So here what we can do, here I am going to give a output as B bar, and here I need a bar. Since I have A here, even though if I include A bar here at the OR operation, it won't affect. So C, A B bar is I am having. So A inside that, right? If I put A bar plus B bar, because I need B bar here. So if I put A bar plus B bar, this will give output like this will multiply with this. For the A into A bar, as we know, it will be 0. So we no need to put 0 in our operation, and A into B bar. So the output will be A into B bar. Same as the case with the A bar B. So here A bar B. Same as the case with A bar B. So here we have our B here, and instead of A, here also same A bar plus B bar, what we have used here, we are going to use. So it will be B bar, B, A bar. B into B bar will become 0 here. So now we got a bar B and A B bar at our thing, right? So, okay, now what we have done, okay, actually we have multiplied this with, we have A bar with A bar, we have just multiplied this A bar B with A, okay, A B bar with A and A bar B with B to get this one, and this also we need, right? A bar plus B bar is the first NAND gate we are expecting. So as per the De Morgan's theorem, right? Here if you see, A bar plus B bar will be the A dot be the whole bar. So it will be the A be the whole bar. So the first NAND gate will be the A bar plus B the whole bar, A bar plus B bar, so that is A B the whole bar. And this one, to make A B bar the whole bar, what we need here, A at the A B bar the whole bar, we need A at this one. So we will be just doing, okay, this NAND gate again, because AND only we are talking about. Before that we just removed our NAND gate. Okay, same as that here, it will be the NAND gate which will give you the A bar B the whole bar. Okay, so here it will be A, and here it will be B. So AB the whole bar, that means here we are seeing A bar plus B bar, and here after multiplication here A and here here it is B. So if we multiply this with this A bar B and plus this one will get, and again we'll just not operation will do, so we will be having A bar B the whole bar, and here also same is the case. So if you see here, this will be B, this will be A, B, this one. So here we just implemented our NAND gate, a XOR gate using only 4. Okay, I think it's clear. It clear, I think so. Okay, this is about XOR. Okay, so here if you see, right, we have used only 4 gates. So we could have one more gate also, like with the 4 gate, instead of 4 gate we can have it like 5 gates also. That how the circuit will be look like, the output will be same. So here we will be expecting the AB bar the whole bar, and here we will be expecting A bar B the whole bar. So for your previous NAND gate, what you need, one input you need A, and one input you need B bar, and here you need one input you need A bar and one input you need B. So ready-made inputs are only A and B, and for A bar and B bar you need another one, because the ready-made, it won't be the ready-made, the A bar and B bar. So what you have to do, again the same input you have to use for the another, you have to use with the another one inverter. For that what you will do, you will just short the NAND gate inputs. So it will go as A bar here, and here also it will be here. So here also the inverted form you will use here to get the B bar. So generally if we have this format, if we implemented using this format, you will be having 5 gates. If we implement using this format, it will be 4 gate. It will be the straightforward, as simple as that, but it will be something we have to think about this theorem and all. So it will give good impression to your interviewer if you are just using this method to implement the XOR gate. Okay. Okay, now XOR gate is okay. And one more thing also, here we'll talk about the XNOR, right? This is same like an NAND, right? This is also the inverted version of the XOR gate. Okay, this is simple as that. We no need to derive anything, since we derived NAND gate now, XOR gate now only, right? So what we could do, so for XNOR gate, as we know, XOR plus not only the XNOR gate, that means we need an NOT gate at the if you put the symbol, it will be this. So at the output you need this one. So what you could do, you could directly simply use the circuit what we have implemented now. Okay, and this one, and this is A, this is B, and here we will be having another one NAND gate, and here we will be having another one NAND gate. It will outright. So here we will be having our A XOR B, and as simple as that, you can add another one inverter, NAND based inverter here to make it as XNOR. Okay, this will need a extra one gate. So this is what the NOR gate implementation using NAND gate. Yeah, only for XOR you can able to derive, and yeah, that is enough. So if this is for the XOR gate implementation and XOR and XNOR implementation using NAND, right? So if we go with NOR, that is exactly the reverse way. Here since we have used the NAND gate, we just implemented XOR, then we went to XNOR. But in case of NOR, we'll use first XNOR, we'll implement, then we'll go with the XOR. This is because that sum of product and product of sum, right? Because of that format we are doing that one. So yeah, this is what we will be. So in the next video we will cover the XOR and XNOR implementation using NOR gate. Thank you. Thanks for watching.